Hi dear students, this particular class I am going to introduce the maxima and minima ideas. So a function f, we can say f of x, defined on an interval I. F of x be a function defined on an interval I. There exists a real number a belongs to I such that f of x less than or equals to f of a for all x belongs to I. Then we say that f of a is the maximum value of the function in the interval I. At the same time, let f be a real valued function defined on an interval I, and there exists a real number a belongs to I such that f of x greater than or equals to f of a. F of x greater than or equals to f of a. Then we say that f of a is the minimum value of the function. This has to satisfy for all x belongs to I. Then we say that f of a is the minimum value in this case, and in this case we can say f of a is the maximum value of that function. With this idea, we will try to discuss a few applications. Suppose you see a problem is given like this: minus x minus 1 whole square plus 5, that is the function given f of x is equals to. Right? Now we know that square of a number x minus 1 whole square is always greater than or equals to 0. Now multiply with minus. Whenever we are multiplying with minus, inequality changes. That's why minus of x minus 1 whole square less than or equal to 0. Now add 5 throughout the inequality. Minus x minus 1 whole square plus 5 is less than or equals to 5. So what the information we got? F of x is always less than or equals to 5. F of x less than or equals to 5 means we can say the maximum value of this function is equal to 5. Suppose the problem is given in this way: f of x is equals to x minus 2 whole square plus 10 given, right? So we know that x minus 2 whole square is always greater than or equal to 0, because the square of a number is always greater than or equals to 0. Now add both sides 10, then we will get x minus 2 whole square plus 10 is greater than or equals to 10. Now we can say this one as f of x greater than or equals to 10. But f of x greater than or equals to 10 means we can say this function has a minimum value 10, right? When you will get that minimum value? Yes, you will get that minimum value 10 when x is equals to 2. When you will get the maximum value 5? Yes, we will get that maximum value 5 when x is equals to 1. So in this case the function has a minimum value 10, greater than or equals to 10, minimum is 10, but there is no maxima for that function. Whereas in this case f of x less than or equals to 5, maximum value is equal to 5 and it will go up to minus infinity. That's why we can say there is no minima for that function. Now we have another example here. I am taking f of x is equals to we can take sine 2x plus 5. Now here we know that minus 1 less than or equals to sine 2x is less than or equals to 1. Sine 2x is always lies in between minus 1 and plus 1. Now what we can say here? Add 5. Throughout the inequality we are adding 5. 4 less than or equals to sine 2x plus 5, which is nothing but the given function, is less than or equal to 6. Now I can say 4 less than or equals to f of x less than or equal to 6, we can say. That means this function, that means the given function has a maximum value 6 and the minimum value 4. Maximum value is also there, minimum value is also there for that function. Suppose the function now it is given like this: f of x is equal to x cube plus 5. Now what happens here? As x values are tending to minus infinity, f of x values also tending to minus infinity. At the same time, whenever x values are tending to plus infinity, f of x values also tending to plus infinity. So that's why for this function there is no maxima and no minima, right? So the first case we discussed functions with minima, no maxima. Second case we discussed the function has a maxima but no minima. And the third case we discussed the maximum value, minimum value both exist. And this is the another case, there is no maxima and no minima for the given function. So now next I am going to discuss about the first derivative test for finding local maxima and local minimum value of a function. So observe here, this is the function. Let f of x be a function defined on an interval I. This is at x is equals to a. X is equals to a is said to be a local minimum value of the function. X is equal to a is said to be a local minimum value of the function. This is the first point has to satisfy. F dash of a must be equal to 0, no doubt. At x is equal to a, if you draw a tangent, the tangent is parallel to x-axis. Tangent is parallel to x-axis means slope 0, right? So no doubt f dash of a is equal to 0. Now you can observe to the left side of a, to the left side of a, anywhere you draw a tangent to the curve, anywhere you can draw to the left side of a. To the left side of a, we are drawing a tangent. That tangent makes an angle theta with x-axis. Now tell me that theta is an acute angle or obtuse angle? No doubt, inclination is an obtuse angle. Inclination is an obtuse angle means tan theta is negative. Tan theta is negative means f dash of x we will get less than 0. So what is the meaning of that? To the left side of a, to the left side of a, f dash we are getting negative. Next, at the same time, to the right side of a, anywhere draw a tangent to the curve. This is the tangent drawn to the right side of a. Now the tangent makes an angle alpha. Tell me that alpha is an acute angle or obtuse angle? No doubt, alpha is an acute angle. But alpha is an acute angle means tan alpha is positive. And tan alpha is positive means what we can say? Slope positive means we can say f dash of x is greater than 0. So what happens here? To the left of a, f dash of x is negative. To the right of a, f dash of x is positive. So that means as x values are increasing through a, you can observe we are passing through a. As x values are increasing through a, f dash of x changes its sign from negative to positive. Greater than 0 means positive, less than 0 means negative. So again, as x values are increasing through a, as x values are increasing through a, f dash of x changes its sign from negative to positive. But negative to positive means at this point we have, at x is equal to a, we have a local minimum value for the function, right? Once again, as x values are increasing through a, f dash of x changes its sign from negative to positive. F dash of x changes its sign from negative to positive. Then x is equals to a is a point of, x is equals to a is a point of local minima. And that local minimum value, and that local minimum value is equals to f of a. In the given function, put x is equals to a, we will get the local minimum value, right? So that is about the local minima finding by using first derivative test, right? Once again you can check, as x values are increasing through a, f dash of x changes its sign from negative to positive. negative to positive, then x is equal to a is a point of local minima, and the local minimum value is equals to f of a. Next we are going to discuss about the local maxima idea. So you can observe this is the graph of one particular function. So if you observe the graph can extend like this. It has no minima but it has a maximum value. The graph is not crossing this particular point. It has a maximum value. Right. At x is equal to a, you can observe this is x is equals to a. At x is equals to a, the function, no doubt it has a maximum value. Now you can check to the left side of a. To the left side of a, anywhere you draw a tangent, that tangent makes an acute angle theta with a positive direction of x-axis. That means theta is the inclination. Inclination is an acute. That's why we will get a tan theta positive. Tan theta positive means we can say f dash of x greater than 0. Next, observe to the right side of a. To the right side of a, anywhere draw a tangent to the curve. This is the tangent drawn to the curve to the right side of a. Now the tangents makes an angle alpha. No doubt that alpha is an obtuse angle. Alpha is an obtuse angle means I can say tan alpha you will get negative. Tan alpha negative means tan alpha is nothing but the slope. That means we are getting f dash of x less than 0. Now what we are observing? As x values are increasing through a, f dash of x changes its sign from positive to negative. As x values are increasing through a, f dash of x changes its sign from positive to negative. Then x is equals to a is a point of local maxima. X is equal to a is a point of local maxima, and that local maximum value is equals to f of a. Sir, here why you are not calling maxima and minima? Why you are calling local maxima and local minima? There is a reason for that. You can observe here. Suppose one particular graph of a function we got like this. Right? Now you can observe this is x is equal to say a1, and x is equals to a2, and here x is equals to a3. Now around in the neighborhood of a1 we are talking about. That means in this local area, when we are observing in this area, that means in the neighborhood of a1, this is the maximum value, but this is not the maximum value of the entire function. So in the neighborhood of a1, this is the maximum value. In the neighborhood of a2, this is the minimum value, but this is not the minimum value of the entire function. Entire function has a minimum value here also, but in this local area, this is the minimum value. In this local area, that is the maximum value of the function. That is the reason we are using the terminology local maxima and local minima. So in the neighborhood of a1, that is the maximum value. In the neighborhood of a2, that is the minimum value. In the neighborhood of a3, that is the maximum value. That is about the local maxima and local minima. Right? So okay, you are saying that f dash of x changes its sign from positive to negative means local maxima. F dash of x changes its sign from negative to positive means local minima. If f dash of x does not changes its sign, then that point is called point of inflection. F dash of x does not changes its sign, then we will call that point as point of inflection. That means as x values are increasing through a, f dash of x does not changes its sign, then that particular point is called point of inflection. So just can take a few applications based on this particular first derivative test. So this is the question given. F of x is equals to x cube minus 6x square plus 9x minus 8. That is the function given. Now find out f dash of x. What is f dash of x? F dash of x is equal to 3x square minus 12x plus 9. So if you take 3 common, then you will get x square minus 4x plus 3. We can factorize it as x minus 1 into x minus 3 is the factorization. Now we can represent on the number line. This is 1 and this is 3. You know wave curve method, plus minus plus. Now you can observe as x values are increasing through 1. As x values are increasing through 1. As x values are increasing through 1, f dash of x changes its sign from positive to negative. F dash of x changes its sign from positive to negative. Therefore, x is equals to 1 is a point of local maxima. Therefore, the local maximum value is equals to f of 1. What to do? This 1 we have to substitute in the given function. So that is nothing but 1 minus 6 plus 9 minus 8. That is the local maximum value of the function. At the same time, you can observe as x values are increasing through 3, as x values are increasing through 3, f dash of x changes its sign from negative to positive. As x values are increasing through 3, f dash of x changes its sign from negative to positive. Negative to positive. Therefore, x is equal to 3 is a point of negative to positive. X is equals to 3 is a point of local minima. Therefore, that local minimum value is equal to f of 3. That means x is equal to 3. We have to substitute in the given function. That is nothing but f of 3 is equal to 3 cube minus 6 into 3 square plus 9 into 3 minus 8. So that is about the local minimum value of the function, and this is the local maximum value of the function. So that is the way of finding local maxima and local minima by using first derivative test. So another example you can see. So this is one more example. The function is given in this way. F of x is equals to x minus 2 whole to the power of 4 into x plus 1 whole cube. X minus 2 whole to the power of 4 into x plus 1 whole cube. That is the function f of x. Come on, find out f dash of x. F dash of x is equal to, we have to apply UV rule. X minus 2 whole to the power of 4 into x plus 1 whole cube differentiation is 3 into x plus 1 whole square plus again x plus 1 whole cube into x minus 2 whole to the power of 4 differentiation 4 into x minus 2 whole cube. Now what we can take common here? We can take x minus 2 whole cube common. Next we can take x plus 1 whole square also common. Then what left? So after taking x minus 2 whole cube common, then we left with 3 into x minus 2. Next, here we took x plus 1 whole square common and x minus 2 whole cube common. Then we left with 4 into x plus 1. So here we left with 4 into x plus 1 and here we left with 3 into x minus 2. Now the simplification we can write it as x minus 2 whole cube into x plus 1 whole square into 7x minus 6 plus 4, right? So therefore we are getting 7x minus 2. Again this can be written as x minus 2 whole square into x plus 1 whole square into x minus 2 into 7x minus 2. I hope so everyone followed what I did. So this x minus 2 whole cube can be written as x minus 2 whole square into x minus 2. Now you can observe this total expression is positive or negative depends only on these two terms. If these two terms are positive, then expression is positive. If these two terms are negative, then expression is negative, because square of a number is always positive. That's why now observe here on the number line. This is equated to 0, x is equals to 2. This is equated to 0, x is equals to 2 by 7. Now this is the point we are representing 2 by 7. Next x is equals to 2. Somewhere here we have minus 1 is also there. Give it that one. It's not required. Afterwards we will see. Okay, now we come with that. This is a plus, minus, plus. What happens here? This is a 2, this is 2 by 7, and here now show minus 1. Observe, as x values are increasing through 2 by 7, as x values are increasing through 2 by 7, f dash of x changes its sign from positive to negative. Therefore, x is equals to 2 by 7 is a point of local maxima. X is equals to 2 by 7 is a point of local maxima, and the local maximum value, that local maximum value is equals to f of 2 by 7. So that's why this x value 2 by 7 we have to substitute in this given equation, in the given function. Next you can observe, as x values are increasing through 2, f dash of x changes its sign from negative to positive. As x values are increasing through 2, f dash of x changes its sign from negative to positive. Negative to positive means at x is equals to 2, the function has local minima. So we have to find out that local minimum value. So that local minimum value, is equals to f of 2. So that's why x is equals to 2, we have to substitute in the given function, right? So this is the local minimum value and this is the local maximum value at 2 by 7. But what about minus 1? X is equal to minus 1. You can observe, as x values are increasing through minus 1, that means to the left of minus 1 also positive, to the right of minus 1 also positive. That's why as x values are increasing through minus 1, f dash of x does not changes its sign. That's why x is equal to minus 1 is the point of inflection. Okay. So that is about the first derivative test and applications on first derivative test. How to find out the local maxima and local minima by using the first derivative test. Next I am going to discuss about the second derivative test for local maxima and local minima. So let f be a differentiable function on interval I and a belongs to I. So x is equals to a, find out f dash of a. Note out f dash of a is equal to 0 and f double dash of a exists. F double dash of a exists and not equal to 0. Let f be a function differentiable on an interval I and a belongs to this interval I. F dash of a is equal to 0 and f double dash of a has to exist and not equal to 0. Then the first point is f double dash of a, f double dash of a greater than 0. F double dash of a value has to exist but not equal to 0. F double dash of a greater than 0, then we say that at x is equals to a, at x is equals to a, function has minimum value. At x is equal to a, function has a minimum value and that minimum value is given by f of a. Second derivative greater than 0 means minima. Why? All of you observe here. What happens here? We got the information f dash of a is equals to 0. That is the information we got. And we are saying that f double dash of a greater than 0. And f, once again, f dash of x greater than 0 means what we are saying? The function is an increasing function. Which function? F of x is an increasing function. F dash of x greater than 0 means f of x is an increasing function. Now, f double dash of a greater than 0, what it means? F double dash of a greater than 0 means in the neighborhood of a, f dash is an increasing function. Once again, f double dash of a greater than 0 means in the neighborhood of a, f dash is an increasing function. But f dash is an increasing function in the neighborhood of a, and we got f dash of a value is equal to 0, but it is an increasing function. Definitely at a we got 0 f dash, but it is increasing function. A plus must be positive, a minus must be negative. Once again, f double dash of a greater than 0 means in the neighborhood of a, f dash of x is an increasing function, and we got the information f dash of a is equal to 0. But f dash of a is equal to 0 means what can you say about f dash of a minus? Negative. What can you say about f dash of a plus? Must be positive. The reason is it is an increasing function. Increasing function. Right? Now what happens? As x values are increasing through a, f dash changes its sign from negative to positive. As x values are increasing through a, f dash changes its sign from negative to positive. When negative to positive means we have local minima. So that is the reason at x is equals to a, function has local minimum value. At the same time, the second point here what we are going to discuss is if f double dash of a less than 0, second derivative less than 0, then what we can say at x is equals to a, function has local maximum value. Function has local maximum value, and that local maximum value is given by f of a. So observe here, same discussion again, f double dash of a less than 0. F double dash of a less than 0 means what can you say about the function f dash of x in the neighborhood of a? F dash of x is a decreasing function in the neighborhood of a. It is a decreasing function in the neighborhood of a, but we have the information f dash of a value is equal to 0. F dash of a value is equal to 0, but it is a decreasing function. But when it is a decreasing function, to the left side of a it must be positive because it is a decreasing function. To the left side of a it must be positive, to the right side of a it must be negative. Right? Because it is a decreasing function. Why it is a decreasing function? F double dash of a we got less than 0. But f double dash of a less than 0 means f dash is a decreasing function in the neighborhood of a. But f dash of a value already 0 given. That's why to the left of a it must be positive, to the right of a it must be negative. Now what happens? As x values are increasing through a, f dash changes its sign from positive to negative. So positive to negative means x is equals to a is a point of local maxima. So that is the second derivative test, or we can say this one as higher derivative test for finding local maxima and local minima. So say take the same example which we discussed earlier. F of x is equal to x cube minus 6x square plus 9x minus 8. That is the function. The same function we discussed with the help of the first derivative test. Now the same problem we are going to discuss with the help of the second derivative test. Come on, find out f dash of x. F dash of x is equal to 3x square minus 12x plus 9. That is f dash of x. Now equate to 0, you will get 3 into x square minus 4x plus 3. That is equals to 3 into x minus 1 into x minus 3. If equated to 0, we are getting the values of x is equals to 1 comma 3. Next what to do? We have to find out double derivative. Second derivative, find out f double dash of x. Now f double dash of x is equal to 3 into 2x minus 4. That is f double dash of x. Now find out f double dash of 1. F double dash of 1 find out. F double dash of 1 is equal to 3 into 2 minus 4, no doubt, which is less than 0. Or a second derivative less than 0 means, therefore at x is equals to 1, f has local maxima. Therefore local maximum value is equal to f of 1. So this x is equal to 1. We have to substitute in the given function. Next, in the similar way, we have to find out f double dash of 3 also. Now find out f double dash of 3. F double dash of 3 is equals to 3 into 6 minus 4. No doubt this value greater than 0. Second derivative greater than 0 means we have a local minima. Therefore, at x is equal to 3. At x is equal to 3, f has local minima. Therefore, that local minimum value is equal to f of 3. That means this x is equal to 3. We have to substitute in the given function so that you will get the local minimum value. Once again, second derivative less than 0 means local maxima. Second derivative greater than 0 means local minima. But where the second derivative becomes 0, if second derivative becomes 0, the second derivative test fails. F double dash of x is equal to 0. At that point second derivative test fails. Then we have to go for the first derivative test only. So that is about the local maxima and local minima finding by using the second derivative test, which we will also call it as higher order derivative test. Now the other information is how to find out the maximum and minimum value of the function. Now I am not talking about local maxima and local minima. I am talking about the global maximum value and the global minimum value of the function in closed interval a comma b. That means he has given some boundary. In that boundary, he is asking the local maxima and local minima. He is asking maximum value and minimum value of the function. That's what we will call it as global maxima and global minimum value of the function in the interval. In this interval, we have to find out the maximum value and the minimum value of the function. So for that, what we have to do is, first of all, differentiate the function f dash of x. F dash of x equate to 0, you will get x value, suppose alpha, beta, gamma. F dash of x equated to 0, suppose you got the values of x as alpha, beta, gamma. Check among these values which values are present in this interval. Okay, alpha present in that interval, beta is also present in that interval, but gamma is not there in that interval. When gamma is not there in that interval, forget about the gamma, because gamma is beyond the boundary. He is asking to find maxima and minima value in that boundary only. So that's why forget about gamma. Now what to do? Find out f of a value, end point of the interval. Find out f of alpha value. Find out f of beta value. And find out f of b value. No need to bother about gamma, because gamma is not in our range. Gamma is outside to this boundary. So f of a we are finding, f of alpha, f of beta we are finding. Why we are finding? These two present in this interval. So then we are finding the other end point, f of b. Among all these values, which is the maximum? that is called the global maximum value of the function. That is called absolute maximum value of the function. Among all these values, which is a minimum? That is called the global minimum value of the function, or we can say absolute minimum value of the given function. So that is the way of finding global maxima and global minima of the function in closed interval a comma b. So let's discuss one question based on this particular idea. So the question is given like this: f of x is equals to 2x cube minus 15x square plus 36x plus 1 in closed interval 1 comma 5. He is asking to find the maximum and minimum value. Now find out f dash of x. F dash of x is equal to 6x square minus 30x plus 36. That is differentiation. Now this differentiation equated to 0, what we will get? X square minus 5x plus 6 you will get. So that is equated to 0. We are getting x value is equals to 2 comma 3. Now check, these two values present in this interval or not? Yes, both the values are there in that interval. Now what to do? We have to find out f of 1. F of 1 is equals to 2 minus 15 plus 36 plus 1. That is f of 1 value. So that is nothing but 37 plus 2, 39. 39 minus 15, you will get 24. Right? Next we have to find out f of 2. F of 2 is equals to 2 into 2 cube, that is 8 2s are 16, minus 60 plus 72 plus 1. Next find out f of 3. F of 3 is equal to 3 cube 27 2s 54 minus 3 square is equal to 9 135 plus 36 into 3 is equals to 108 plus 1. Next we have to find out f of 5. So f of 5 is equals to, so 5 cube 125 into 2 is equals to 250 minus 25 into 5. 25 into 5 how much? So 25, 250, 375 minus 36 into 25 plus 1. Now check, among all these values, which value is a maximum? That is the global maximum value of the function. Which value is a minimum value? That is the global minimum value of the function in the given interval. So that is the way of finding global maxima and global minima value of the function in the given interval. So now again I am going to discuss here concavity. So concavity of the given curve. So what is concave upward? First of all, now this is the meaning of concave upward. Anywhere you draw a tangent to this curve, anywhere draw a tangent to the curve, if the tangent lies completely below the curve, then it is said to be concave upward. Anywhere you can draw a tangent, the tangent completely lies below the curve. So for concavity upward, definitely we have to get f double dash of x, greater than 0. F double dash of x greater than 0. You see, when the curve is there like this, it has a minima value or not? Minima value, second derivative greater than 0 or not? So that's why for concavity upward, f double dash of x greater than 0. So concave upward, what is the meaning for that? Or the same we can also say it as convex down. Convex down, or we can say concave upward. So concave upward means anywhere you draw a tangent, the tangent completely lies below the curve, then it is said to be concave upward. The graph is concave upward. For concave upward, f double dash of x is greater than 0. Next one is this one, we will call it as a concave downward. Concave downward means anywhere you draw a tangent, the tangent lies completely above the curve. The tangent lies completely above the curve. Then this is said to be concave down. or we can say it as convex up. Okay, so this is a concave upward and this is concave downward. In case of concave downward, f double dash of x must be less than 0. F double dash of x must be less than 0. Where f double dash of x is equal to 0 or f double dash of x does not exist. Where f double dash of x is equal to 0 or where f double dash of x does not exist, then the curve, the concavity changes. You can observe the graph of f of x is equal to x cube. Can you tell me its differentiation? F dash of x is equal to 3x square and f double dash of x is equals to, you will get a 6x. When x is equal to 0, it becomes 0 or not? So where double differentiation is equal to 0, then the curve changes its concavity. This is up to here, it is a concave, come on, it is concave downward. Now from concave downwards to, it changes to concave upward. This is the key idea in drawing the graphs. Okay, so at 0, double differentiation becomes 0. Right? Now the curve concave downward to concave upward. So it changes its concavity at where the double differentiation becomes 0 or f double dash of x does not exist. So another point here we are going to discuss about a critical point. So what are critical points? So where f dash of x is equal to 0 or f dash of x does not exist. F dash of x is equal to 0 or f dash of x does not exist. Those points are called as critical point. Where differentiation is equal to 0 or where differentiation does not exist, those points are called as critical points. Now you can see, this is the graph of one particular one. We can say this point is a critical point, this point is a critical point. Let us say this is c comma f of c, and you can say this one as c1 comma f of c1. So these points are called critical points where differentiation is equal to 0. At the same time, where the differentiation does not exist, that is the graph of mod x, where the differentiation does not exist, this point is also called as a critical point. You can see whether the graph of one function is there like this. This is the graph of the function. Now this point is also called as a critical point where f dash of x does not exist or where f dash of x becomes 0, because here horizontal tangent is possible. Here horizontal tangent is possible. That point is called critical point. Okay. So next one we are going to discuss what is a stationary point. Stationary point means where the differentiation becomes 0. Where f dash of x is equal to 0. F dash of x is equal to 0, that point is called a stationary point, or we can call it as a turning point. Yes, that point is called a turning point. You can see this is the graph of one particular function. Now at this point differentiation is equal to 0. So these values are called stationary values. Suppose this is x is equal to a. Then this point we can call it as a comma f of a. That point is called a stationary point, or we can say it as a turning point. Okay, where it has a maximum value, where it has a minimum value, maximum value. These points are called as stationary points, or this value is called stationary value, or we can also call it as turning points or turning values. So no doubt this stationary point is a critical point also. Every stationary point is a critical point, but converse is not true. Every stationary point is a critical point. But what about this point? That point is called point of inflection. What we'll call point of inflection. Why we are calling this one as a point of inflection? Concavity changes. Concavity changes means f double dash of x is becoming 0. So this point is called, because this is concave upward, it is changing now. This is concave downward, it is changing to concave upward. So where the concavity changes, that point is called the point of inflection. Okay, so that is the discussion regarding all these ideas in maxima and minima. Next class we are going to discuss about the applications on maxima, minima, level 1, level 2, level 3, like that we will discuss, and then we are going to discuss the mixed problems on monotonicity and maxima, minima. Really interesting. That is the real calculus involved in that. Okay, thank you, bye bye.